There is a structure in the universe so large that the Milky Way, with all its hundreds of billions of stars, occupies a space within it that is barely worth measuring. It is called the cosmic web, and it is not a metaphor. It is a physical arrangement of matter, filaments, clusters, and voids that spans the observable universe in every direction. We are going to move through this structure one layer at a time. We will begin at the smallest scales and work outward, through galaxy clusters and superclusters, through the great walls and the great voids, until we reach the structures at the very edge of what current science can detect and map. Along the way, we will stop at Laniakea, the supercluster that contains our galaxy, and consider what it means to have an address in something this vast. Tonight, we will journey through each of these regions and explore the edge of what is known. Welcome to Sleepy Time Universe, where we explore the cosmos at a pace designed for rest and reflection. Chapter 1. What the universe looks like from the outside. If you could leave the universe, step outside it entirely, and look back from some impossible vantage point, what you would see would not look like a cloud of galaxies scattered evenly in every direction. It would look like a web, not a perfect web, not a symmetrical one, but something organic and sprawling. Bright threads running across enormous distances, connecting at dense glowing points, surrounding regions of near total darkness that stretch for hundreds of millions of light years without a single galaxy to interrupt them. The overall impression would be something between a neural network and the structure of a sponge, porous, interconnected, and arranged according to rules that took billions of years to establish. This is not an artist's impression. It is not a simplified diagram made for textbooks. It is what the universe actually looks like when you map it at sufficient scale, and astronomers have been building that map, piece by careful piece, for several decades now. The cosmic web is one of the most important discoveries in the history of cosmology, not because it was unexpected in every detail, but because seeing it confirmed something profound about the nature of gravity, matter, and time working together across distances that have no human equivalent. To understand why the universe is structured this way, it helps to start not with the present, but with the very beginning. The cosmic web did not appear fully formed. It grew. It assembled itself slowly over billions of years from conditions that existed in the first fractions of a second after the universe came into being. And the fact that it exists at all, that matter is arranged in filaments and clusters rather than spread uniformly in every direction, tells us something fundamental about the physics that governed everything from the very start. But before we trace that history, it is worth spending some time simply appreciating the scale of what we are talking about. Because one of the difficulties with the cosmic web is that the human mind has no natural reference point for distances of this magnitude. We are accustomed to thinking about space in terms of the solar system, or perhaps the Milky Way. The cosmic web operates on scales that make the Milky Way feel like a single grain of sand on a very long beach. The Milky Way is roughly 100,000 light-years across. That is already a number that resists easy comprehension. Light, moving at nearly 300,000 kilometers per second, takes 100,000 years to cross our galaxy from one side to the other. And yet, when astronomers map the cosmic web, they work in units of millions and hundreds of millions of light years. The filaments that form the threads of the web can stretch for 300 million light years or more. The voids enclosed within the web can be 200 million light years across. The superclusters that mark the brightest nodes of the web span hundreds of millions of light years in every direction. At these scales, individual galaxies are not landmarks. They are data points. The Milky Way, the Andromeda Galaxy, the dozens of smaller galaxies that make up our local group. All of them together occupy a region of space that, on a map of the cosmic web, would be represented by a dot so small it would be difficult to see. This is not said to diminish what those galaxies are. Each one contains hundreds of billions of stars, and around many of those stars orbit planets, and on at least one of those planets something has arisen that is capable of looking outward and asking what is out there. That is remarkable by any measure. But the cosmic web asks us to hold that smallness in mind, to sit with it quietly and let the scale settle rather than rushing past it toward the next fact. There is a particular kind of stillness that comes from genuinely reckoning with distances of this size. It is not an unsettling stillness. It is more like the feeling of standing at the edge of something very large and simply being present with it. The ocean at night, perhaps, or a mountain range seen from a great distance. The scale does not threaten. It simply expands the sense of what is possible, of how much exists, of how much has been quietly in place all along without our knowing. Astronomers who work with the cosmic web professionally describe something similar. The data arrives as numbers, as redshift measurements and coordinate positions, and yet when those numbers are rendered into images, when the filaments take visual form against the darkness, there is often a pause, a moment of adjustment, because what the data reveals looks less like a scientific result and more like something that has always been there, waiting to be seen. The first serious maps of large-scale structure began to emerge in the 1980s, when astronomers conducting systematic surveys of galaxy positions noticed that galaxies were not distributed randomly. They were clustered. They formed chains and sheets. Between those chains were enormous empty regions. The universe, it turned out, had texture, a texture that had been invisible as long as astronomers were looking at individual galaxies in isolation, but became unmistakable once enough positions had been plotted together. One of the earliest clear demonstrations of this came from the work of Margaret Geller and John Huchra at the Harvard-Smithsonian Center for Astrophysics, who in 1986 published a map showing a slice of the nearby universe that revealed, unmistakably, a filamentary pattern. There was a particularly prominent feature in that map that came to be called the Great Wall, a sheet of galaxies stretching across the survey like a curtain. It was not the largest structure that would eventually be found, but it was among the first to make clear that the universe had organized itself on scales far beyond anything previously appreciated. Since then, surveys have grown vastly larger and more precise. The Sloan Digital Sky Survey, which began collecting data in 2000, mapped the positions of hundreds of millions of galaxies across a significant portion of the sky and produced images of the cosmic web that remain among the most striking in all of science. More recent surveys have pushed further still, mapping structure at greater distances and with greater resolution, revealing a web that grows more intricate the more carefully it is examined. What all of these surveys confirm is the same basic picture. The universe is not uniform. It is not a smooth distribution of matter thinning gradually towards some distant edge. It is structured hierarchically and persistently, from the scale of galaxy groups up through clusters, superclusters, filaments, and walls, all the way to features so large that they sit at the boundary of what current cosmological models can comfortably accommodate. The universe has a shape. It is not a shape that fits comfortably in the imagination, but it is a real shape built from real physics, and over the course of this video, we are going to explore it together, one layer at a time, moving slowly and without hurry, through one of the most astonishing structures that has ever been found. Chapter 2. How structure formed from nothing. The cosmic web is ancient. Its roots reach back to the first moments of the universe, to conditions so extreme and so remote from everyday experience that they require a different kind of patience to consider. Not the patience of waiting for something to happen, but the patience of sitting with ideas that have no familiar equivalent and allowing them to become gradually less strange. In the very beginning, the universe was not empty. It was the opposite of empty. All of the matter and energy that exists today was compressed into a space incomprehensibly smaller than anything we can point to, at a temperature and density that current physics can approach, but not fully describe. This was not a point sitting inside a larger space. Space itself was that point. Everything that would eventually become galaxies, filaments, superclusters, and voids was contained within it, undifferentiated and unstructured. Then it expanded. The expansion of the universe is not like an explosion in the conventional sense. An explosion moves outward from a central point into surrounding space. The expansion of the universe has no center and no surrounding space to expand into. Space itself stretched, carrying everything within it along for the journey. And as it stretched, it cooled. And as it cooled, the conditions that had kept matter in a uniform, undifferentiated state began to change. For the first few 100,000 years, the universe was so hot and dense that matter and radiation were locked together in a kind of plasma. Photons could not travel freely. They were constantly scattering off charged particles, keeping everything mixed and bright. There were no atoms yet, no neutral hydrogen, no structures of any kind. Just a glowing, churning sea of particles and energy moving together under conditions that would be fatal to any structure attempting to form. But the universe was not perfectly uniform during this time. There were tiny variations in density, regions that were very slightly more compressed than their surroundings, and regions that were very slightly less compressed. These variations were extraordinarily small. We are talking about fluctuations of roughly 1 part in 100,000. If you were somehow able to take the temperature of the early universe at 2 different points chosen at random, the difference would be almost immeasurably small. And yet, those tiny differences were enough, because gravity is patient, and it works in only one direction. Regions that were slightly denser than average had slightly stronger gravitational pull. Over time, that slightly stronger pull drew in a little more matter from the surrounding areas, which made those regions slightly denser still, which strengthened their gravitational pull further. This process, called gravitational collapse, is self-reinforcing. Once it begins, it continues. Slowly at first, then with increasing momentum, the slightly overdense regions grew denser, while the slightly underdense regions grew emptier. This is the fundamental mechanism behind all large-scale structure in the universe. The cosmic web, with its filaments and clusters and voids, is the product of this process operating over nearly 14 billion years. The seeds were planted in the first fraction of a second. The harvest took the rest of cosmic history to arrive. Around 380,000 years after the beginning, something important happened. The universe had cooled enough that electrons and protons could combine to form neutral hydrogen atoms for the first time. This moment is called recombination, and it had a dramatic effect on the universe's appearance. Suddenly, photons were free to travel without scattering. The universe became transparent. Light could move in straight lines across vast distances for the first time. That light is still traveling today. We detect it as the cosmic microwave background. faint glow of radiation arriving from every direction in the sky, carrying an imprint of the universe as it looked 380,000 years after the beginning. When astronomers map the temperature of the cosmic microwave background in fine detail, they see exactly those tiny fluctuations, the 1 in 100,000 variations in density that were present in the early universe. The seeds of the cosmic web are visible in that map, frozen in light that has been traveling for nearly 14 billion years. After recombination, gravity continued its work in the dark. There were no stars yet, no galaxies, no light sources of any kind. This period is called the Cosmic Dark Ages, and it lasted for several 100 million years. During this time, the density fluctuations that had been imprinted in the early universe continued to grow. Matter flowed slowly along invisible gradients, accumulating where density was highest, draining away from regions where density was lowest. The geometry of this process is not random. The mathematics of gravitational collapse in an expanding universe naturally produces a particular kind of structure. Matter does not simply clump into spheres. It first collapses along one dimension to form sheets, then along a second dimension to form filaments, and finally along all three dimensions to form the dense compact structures we call galaxy clusters. This sequence, sheets, then filaments, then clusters, is called the Zeldovich approximation, named after the Soviet physicist Yakov Zeldovich, who described it mathematically in 1970. It predicts, from first principles, that the large-scale structure of the universe should look like a web. When the first stars ignited, several 100 million years after the beginning, they did so inside clouds of gas that were already beginning to follow the filamentary structure laid down by gravity. The first galaxies formed at the densest intersections of those filaments. As more stars formed and more galaxies assembled, they illuminated a structure that had been building in darkness for hundreds of millions of years. The cosmic web did not form because galaxies exist. Galaxies exist because the cosmic web formed first. This distinction matters. It means that to understand where any galaxy is, including our own, you have to understand the large-scale structure of the universe. A galaxy's position is not arbitrary. It reflects the history of the matter that formed it, the density fluctuations it descended from, the filaments it sits within or near, the gravitational influences that have shaped its path through space over billions of years. Every galaxy is a product of the web, and the web is a product of conditions that were set in the first moments of everything. There is something deeply settling about this. The structures we will explore over the coming hours, the filaments, the voids, the superclusters, the great walls, are not accidents. They are the inevitable result of simple physical laws operating over vast stretches of time. The universe, given gravity and a slight unevenness in its initial conditions, could not have turned out any other way. Chapter 3. Dark Matter and the Invisible Scaffold. There is a problem with the story told in the previous chapter. It is not wrong, but it is incomplete. Because if you run the mathematics of gravitational collapse using only the matter we can see, the stars, the gas, the dust, the galaxies, the numbers do not work out. The universe as we observe it today, with its filaments and clusters and the particular arrangement of the cosmic web, could not have assembled itself in the time available using visible matter alone. There is not enough of it, and it does not behave in quite the right way. Something else is doing most of the work. That something is dark matter, a form of matter that does not emit light, does not reflect light, and does not interact with electromagnetic radiation in any way we have yet been able to detect directly. It cannot be seen. It cannot be imaged. Its presence is inferred entirely from its gravitational effects on the things we can see. And yet it makes up approximately 85% of all the matter in the universe. The stars and galaxies and gas clouds that we think of as the visible universe, everything that has ever been observed through a telescope, represent only about 15% of the matter that actually exists. This is one of the most significant facts in modern cosmology, and it deserves a moment of quiet consideration. The universe we can see is not the universe. It is a thin, luminous tracing laid over a much larger, invisible structure. The way frost on a window reveals the airflow patterns that shaped it. The cosmic web, as stunning as it appears in astronomical surveys, is itself just the visible portion of something deeper and more extensive. Dark matter was not proposed arbitrarily. The evidence for it accumulated over decades from multiple independent lines of observation. One of the earliest came from the astronomer Fritz Zwicky, who in 1933 studied the Coma cluster, a large cluster of galaxies, and found that the galaxies within it were moving far too fast to be held together by the gravitational pull of their visible mass alone. The cluster should have flown apart long ago. Something unseen was providing additional gravitational mass, holding it together. Decades later, the astronomer Vera Rubin and her colleague Kent Ford made detailed measurements of how stars within individual galaxies orbit their galactic centers. According to standard physics, stars further from the center of a galaxy should orbit more slowly, just as the outer planets of the solar system move more slowly than the inner ones. But Rubin and Ford found that stars at the outer edges of galaxies were orbiting just as fast as those near the center, sometimes faster. The rotation curves, as they are called, were flat when they should have been declining. The only explanation that fit the data was that each galaxy was embedded within a much larger halo of invisible mass, extending far beyond the visible disk of stars. These halos of dark matter are not distributed the same way as the visible matter they surround. They are more diffuse, more extended, and they were in place earlier. In the early universe, dark matter began clumping under gravity before ordinary matter could do the same. Ordinary matter at that time was still coupled to radiation. It was part of that hot plasma we described earlier, prevented from collapsing freely by the pressure of photons pushing outward. Dark matter, having no interaction with radiation, was free to begin collapsing immediately. It fell into the gravitational wells created by the density fluctuations in the early universe and began building structure while ordinary matter was still held in place. By the time recombination occurred and ordinary matter was finally free to follow gravity, the dark matter had already assembled a scaffolding, a framework of filaments and halos that ordinary matter then flowed into, like water, finding the channels already carved into a landscape. The cosmic web that we see today in galaxy surveys is, in this sense, a map of where the dark matter went first. Galaxies form where dark matter halos are densest. Filaments of galaxies trace filaments of dark matter. The voids between the filaments are empty of galaxies because the dark matter thinned out there first, leaving nothing for ordinary matter to follow. This scaffolding is sometimes called the cosmic skeleton, and the term is more accurate than it might first appear. Just as a skeleton gives shape to a body while remaining largely invisible beneath the surface, the dark matter framework gives shape to the cosmic web while being entirely undetectable by conventional observation. Remove the dark matter and the universe would be nearly featureless. A thin, nearly uniform distribution of gas with no galaxies, no clusters, no web. The nature of dark matter remains one of the most actively investigated questions in physics. Numerous candidates have been proposed over the decades. Weakly interacting massive particles, known as WIMPs, were for a long time considered the most promising possibility. Particles with mass but negligible interaction with ordinary matter, predicted by extensions of the standard model of particle physics. Extensive experiments designed to detect WIMPs directly, by waiting for one to occasionally interact with a detector deep underground, have so far returned no confirmed signals. Other candidates include axions, extremely light particles originally proposed to solve an unrelated problem in particle physics, and sterile neutrinos, a hypothetical heavier cousin of the known neutrino. There are also proposals that dark matter is not a single particle but a mixture, or that it interacts with itself in ways that leave no trace in ordinary matter detectors. The honest answer, as of now, is that we do not know what dark matter is made of. We know it exists. We know, roughly, how much of it there is. We know how it behaves gravitationally, but its fundamental nature remains unknown. What we do know is that without it, none of what we are going to explore in the rest of this video would exist. The filaments, the clusters, the voids, Laniakea, the great walls, all of it depends on a scaffold that was built by something we cannot see. The visible universe is beautiful, but it is, in a very real sense, a consequence of something invisible that came first. There is a particular kind of humility that this invites, not a discouraging humility, but a clarifying one. The universe is not withholding its secrets out of indifference. It is simply larger and stranger than the tools we have built so far are able to fully illuminate. Dark matter is not a gap in our knowledge so much as a horizon, a boundary beyond which there is clearly more, and toward which the work of science slowly and steadily moves. Chapter 4. Filaments, the threads that connect everything. If you were to take all of the matter in the observable universe and ask where most of it spends its time, the answer would not be inside galaxies. It would not be inside galaxy clusters, or even inside the vast halos of dark matter that surround them. Most of the ordinary matter in the universe, the baryonic matter, made of protons and neutrons and electrons, resides in the filaments, the long, diffuse threads that connect the bright nodes of the cosmic web are not empty corridors between more interesting places. They are themselves among the most significant structures in the universe, and they contain within them a history of how matter has moved across cosmic distances over billions of years. Filaments are not sharp boundaries. They do not have edges in the way that a road has edges. They are gradients, regions where matter becomes progressively denser as you move toward their central axis, and progressively thinner as you move away. The densest part of a filament, running along its core, can contain galaxy groups and smaller clusters strung out like beads on a thread. Moving outward from that core, the density falls off gradually into the surrounding voids. There is no precise line where a filament ends and a void begins. The transition is slow and continuous, like the fading of light at the edge of a shadow. The lengths involved are difficult to hold in mind. A typical filament in the cosmic web might stretch for 50 to 100 million light-years. The largest known filaments extend for several 100 million light-years. To put that in some kind of perspective, the distance from the Milky Way to the Andromeda Galaxy, our nearest large galactic neighbor, a distance that would take 2 million years to cross even at the speed of light, is a small fraction of the length of even a modest filament. The filaments of the cosmic web operate on a scale where entire galaxies, separated by millions of light-years, are neighboring points along the same thread. Matter flows along filaments. This is one of their most important properties, and one of the reasons they are so significant for understanding how galaxies form and evolve. Gas streams inward along filaments toward the dense nodes at their intersections. Dark matter halos grow by accreting material that arrives along these filamentary channels. Galaxies at the centers of those halos are fed by the same streams, receiving gas that has traveled along the filament from far out in the surrounding cosmic web. This process of filamentary accretion is thought to be one of the primary ways that galaxies acquire the material they need to continue forming stars over long periods of time. The gas that fills filaments is not the cold, dense gas found inside galaxies. It is a diffuse, hot plasma called the warm-hot intergalactic medium, sometimes abbreviated as WHIM. This gas has been heated by the gravitational energy released as matter fell into the filamentary structure during the formation of the cosmic web. It sits at temperatures of roughly 10,000 to 10 million degrees, too hot to form stars and too diffuse to radiate efficiently, which is part of why it took so long to detect. For many years, the warm-hot intergalactic medium was predicted by simulations, but difficult to confirm observationally. Its detection required instruments sensitive to X-ray and ultraviolet wavelengths, capable of picking up the faint emission from gas spread across enormous volumes of space. The confirmation of the warm-hot intergalactic medium was significant for reasons beyond simply finding the missing matter. It validated the overall picture of cosmic web formation that had been built up through decades of theoretical work and computer simulation. The simulations had predicted not just the existence of filaments, but their temperature structure, their density profiles, and the way gas moves through them. When observations began to match those predictions in detail, it strengthened confidence that the broad framework of cosmic web theory was correct. Filaments are also environments where galaxy properties are shaped in subtle but measurable ways. Galaxies inside filaments tend to be oriented with their rotation axes aligned along the filament direction, a phenomenon called spin alignment that reflects the way angular momentum is acquired during galaxy formation in a filamentary environment. Galaxies closer to the dense cores of filaments tend to be more massive and to have older stellar populations than those near the edges. The filament is not just a passive corridor, but an active environment that influences the galaxies within it over billions of years. One of the most striking visual demonstrations of filamentary structure comes from the Sloan digital sky survey maps, where slices through the galaxy distribution reveal chains of galaxies extending across the survey volume, in patterns that are immediately recognizable as filamentary even to the untrained eye. These maps, which began to be produced in the early 2000s, made the cosmic web tangible in a way that earlier, smaller surveys could only hint at. Looking at a Sloan map of the galaxy distribution is one of those experiences in astronomy that can produce a genuine sense of recognition. The feeling that you are seeing something real and large and previously hidden, revealed by the patient accumulation of data over many years. Beyond what we have already observed, there is reason to believe that filaments connect structures across even larger scales than current surveys have fully mapped. The largest filaments may serve as bridges between superclusters, channeling matter on scales that approach the limits of what the observable universe can contain within a single connected structure. Whether filaments of this scale constitute true bound structures or simply reflect the large-scale pattern of density fluctuations inherited from the early universe is a question that current and future surveys are beginning to address. For now, it is enough to appreciate what filaments are in the most direct sense. They are the connective tissue of the universe. They are the paths along which matter has traveled for billions of years, the channels through which galaxies have been fed, the threads that give the cosmic web its name. Without them, the universe would be a collection of isolated islands separated by featureless voids. With them, it is a network, vast, ancient, and still quietly moving. Chapter 5. Galaxy Clusters. Where the web pulls tight. There are places in the cosmic web where the filaments converge, where threads arriving from multiple directions meet at a single point, and the matter they have been carrying for billions of years finally comes to rest in the densest concentrations that exist anywhere in the observable universe. These places are called galaxy clusters, and they are among the most extreme environments that nature has produced. A galaxy cluster is not simply a group of galaxies that happen to be near each other. It is a gravitationally bound system, a collection of galaxies, gas, and dark matter that has collapsed together under its own gravity and will remain bound together for the remainder of the universe's history. The galaxies within a cluster are not passing through. They are permanent residents, orbiting within a shared gravitational well that has been deepening for billions of years and will continue to deepen as more material falls in, along the filaments that feed it. The numbers involved in a typical galaxy cluster are staggering in their own right, even before you begin to consider the larger structures they are part of. A large galaxy cluster might contain anywhere from hundreds to thousands of individual galaxies. The total mass of such a cluster, including its dark matter halo, can reach 1,000 trillion times the mass of the Sun, a figure so large that it requires a moment to simply acknowledge before moving on. The dark matter alone typically accounts for roughly 80 to 85% of that total mass. The galaxies themselves, which are the most visually obvious component, represent only a few percent of the whole. The remaining mass, somewhere between 10 and 15%, is not in galaxies at all. It is in the intracluster medium, a vast reservoir of extremely hot gas that fills the space between the galaxies within a cluster. This gas has been heated to temperatures of tens of millions of degrees by the gravitational energy of the cluster's formation. At those temperatures, it glows brightly in X-ray wavelengths, and clusters of galaxies are among the most luminous X-ray sources in the sky. The intracluster medium is not a minor detail of cluster structure. It outweighs all the stars in all the galaxies within the cluster combined. It is the dominant baryonic component of these systems, a sea of superheated plasma in which the galaxies float like relatively small objects in a very large bath. The galaxies within a cluster move through this medium at velocities of hundreds or even thousands of kilometers per second. These are not the gentle, ordered motions of stars orbiting within a galaxy. They are the rapid, somewhat chaotic movements of objects falling through and around a deep gravitational well. A galaxy passing through the center of a large cluster at high velocity will experience a process called ram pressure stripping, in which the intracluster medium acts like a headwind, sweeping gas out of the galaxy's disk as it moves. This stripped gas trails behind the galaxy in long streamers, visible in deep observations as faint wisps extending away from the galaxy's leading edge. The galaxy itself, deprived of its gas reservoir, gradually ceases to form new stars and fades toward a quieter, redder old age. This is one of the ways in which the environment of a galaxy cluster actively shapes the galaxies within it. Clusters are not passive containers. They are transformative environments. Galaxies that fall into clusters change over time, their star formation suppressed, their gas stripped away, their shape sometimes distorted by gravitational interactions with neighboring galaxies or with the overall cluster potential. the elliptical galaxies that dominate the populations of rich clusters, smooth, featureless, composed almost entirely of old red stars, are in many cases the products of this transformation process, their original spiral structure long since disrupted by the violence of cluster life. At the very center of many large clusters sits a particularly massive galaxy called the brightest cluster galaxy, or BCG. These are among the largest and most massive galaxies in the observable universe. They grow to their extraordinary sizes partly through mergers with other galaxies that have lost their orbital energy and spiraled inward toward the cluster center over billions of years. Many brightest cluster galaxies also host active galactic nuclei, supermassive black holes at their centers that periodically accrete material and release enormous amounts of energy in the form of jets and radiation. These jets can heat the surrounding intracluster medium, preventing it from cooling and forming stars, and in doing so, they regulate the growth of the galaxy itself in a feedback loop that operates across hundreds of thousands of light years. The study of galaxy clusters has been central to cosmology for reasons that extend beyond their intrinsic interest as physical systems. Because clusters are the largest gravitationally bound structures in the universe, their abundance, how many clusters exist at a given mass and a given cosmic epoch, is sensitive to the overall matter content of the universe and to the properties of dark energy. Counting clusters across cosmic time and comparing those counts to theoretical predictions has provided some of the most precise independent constraints on cosmological parameters. Clusters are, in this sense, cosmological tools as much as they are astrophysical objects. One of the most famous galaxy clusters in the sky is the Coma cluster, located roughly 320 million light-years from Earth in the direction of the constellation Coma Berenices. It was the Coma cluster that Fritz Zwicky studied in 1933, when he first identified the missing mass problem that would eventually lead to the concept of dark matter. The cluster contains thousands of galaxies and has been studied extensively across virtually every wavelength of the electromagnetic spectrum. Its central region is dominated by two massive elliptical galaxies that sit at the bottom of the cluster's gravitational well, surrounded by a diffuse halo of stars stripped from galaxies that passed too close over billions of years. Other well-studied clusters include the Virgo cluster, the nearest large cluster to our own local group, located approximately 54 million light-years away. The Virgo cluster is the gravitational heart of the Virgo supercluster, the larger structure that our own local group sits within, or rather, sits on the outskirts of. We are not inside the Virgo cluster. We are in its extended gravitational neighborhood, close enough to feel its pull, but far enough to have maintained our distance over the age of the universe. The Virgo cluster itself contains more than 1,000 galaxies, anchored at its center by the giant elliptical galaxy Messier 87, which became famous in 2019 when the Event Horizon Telescope produced the first direct image of a black hole shadow using the supermassive black hole at its core. Clusters like Virgo and Coma are not isolated. They sit at the nodes of the filamentary web, connected to other clusters by the threads we explored in the previous chapter. The filaments feed them. The dark matter halos that surround them extend outward to meet the dark matter of the surrounding web, and the clusters themselves are components of still larger structures, superclusters and walls that we will begin to explore as we continue to zoom out from the dense bright nodes and consider what the web looks like at even greater scales. For now, it is worth resting with what galaxy clusters represent in themselves. They are the places where the universe has been most industrious. where gravity has pulled the hardest and held on the longest, where the most matter has been gathered into the smallest volume, where the most extreme physical processes play out over the longest timescales. They are the endpoints of filaments, the anchors of the web, and in their X-ray glow and their slow internal motions, they carry a record of everything the universe has done to build them. Chapter 6. The Great Voids, Structured Emptiness. Between the filaments and the clusters, between the bright threads and the glowing nodes of the cosmic web, there is something else, something that occupies far more of the universe's volume than all the filaments and clusters combined. Something that, at first consideration, might seem like the absence of structure rather than a feature of it. The voids. A cosmic void is a region of space that contains significantly less matter than the cosmic average. Not empty in the absolute sense. There are galaxies inside voids, and gas, and dark matter, though all in much lower concentrations than in the surrounding web, but underdense enough and large enough that they register as distinct features in the large-scale structure of the universe. Distinct not as exceptions or gaps, but as active, evolving components of the cosmic web, as essential to its architecture as the filaments and clusters that bound them. The scale of cosmic voids is comparable to the scale of the structures that surround them. A typical void in the cosmic web might be 80 to 100 million light-years across. The largest known voids are considerably bigger. The Boötes void, one of the most well-studied large voids in the nearby universe, spans approximately 330 million light-years in diameter. It was discovered in 1981 by Robert Kirshner and colleagues during a survey of galaxy redshifts, when they found a region of sky almost entirely devoid of galaxies across a range of distances that implied a physical extent far beyond anything previously identified. At the time of its discovery, it was so much larger than expected that some astronomers were initially reluctant to accept it as a real feature, rather than a statistical artifact. The Boötes void is real. Subsequent surveys confirmed its existence and refined its boundaries. Inside it, there are a small number of galaxies. Roughly 60 have been catalogued within its boundaries, but the contrast with the surrounding regions is stark. Where the cosmic web outside the void is threaded with filaments and punctuated with clusters, the interior of the Boötes void is a vast, quiet expanse where very little has gathered and very little has happened for a very long time. Understanding why voids exist requires returning to the same process of gravitational collapse that formed the filaments and clusters. In regions of the early universe that were slightly underdense, where matter was marginally less concentrated than the cosmic average, gravity pulled matter outward rather than inward, not because gravity reversed direction, but because the surrounding denser regions exerted a stronger net pull on the matter near the void's boundaries than the void's interior could. Matter drained away from underdense regions toward overdense ones. As it did, the underdense regions became emptier still, which reduced their gravitational influence further, which accelerated the drainage. The same self-reinforcing process that caused overdense regions to grow denser caused underdense regions to grow emptier. This means that voids are not simply the spaces left behind after matter moves somewhere else. They are the product of the same gravitational dynamics that built the filaments and clusters. The void and the filament are two aspects of the same process, inseparable and complementary. You cannot have the web without the voids, because the matter that built the web had to come from somewhere, and the voids are where it came from. Inside a void, the environment is as different from a galaxy cluster as it is possible to be, while still existing within the same universe. The matter density is a small fraction of the cosmic average. Dark matter halos are rare and small. Galaxies that do exist within voids tend to be isolated, relatively low in mass, and rich in gas. They have not been processed by the dense environments of clusters and filaments, and so they retain properties closer to what galaxies looked like in the earlier universe. In this sense, void galaxies are something like fossils. They offer a window into conditions that have been largely erased elsewhere by billions of years of environmental processing. The expansion of the universe affects voids differently than it affects the denser structures around them. In regions of average or above average density, the gravitational attraction of matter works against the expansion, slowing it locally. In voids, where matter is sparse and gravity is weak, the expansion of the universe proceeds more freely. Voids expand. They grow larger over time, pushing outward against the filaments and walls that bound them, compressing matter further into the structures at their edges. The filaments and walls that mark the boundaries of voids are in part the product of this outward pressure. Sheets of matter squeeze between expanding voids on either side. This dynamic gives the cosmic web a quality of slow motion that is easy to overlook when thinking of it as a static structure. The web is not frozen. It is evolving continuously on timescales so long that no human observation could capture the movement directly. Voids are growing. Filaments are thinning as matter drains toward clusters. Clusters are growing more massive as they accrete material from the filaments that feed them. The web we see today is a snapshot of a process that began nearly 14 billion years ago and will continue long after the universe has changed beyond recognition. There is something quietly profound about spending time with the voids. They are the majority of the universe by volume. Estimates suggest that voids account for roughly 80% of the total volume of the observable universe, with all the filaments, walls, and clusters compressed into the remaining 20%. The universe is, in this sense, mostly void, mostly a vast, gently expanding emptiness punctuated by the thin, bright web of matter that we tend to think of as the universe's substance. But the voids are not nothing. They have shape, defined by the filaments and walls that surround them. They have history, stretching back to the underdense seeds in the early universe from which they grew. They have dynamics, expanding and pressing against the surrounding structure. And they contain, scattered thinly across their interiors, galaxies that have lived quiet and largely undisturbed lives far from the busier regions of the web. The emptiness of a void is not the same as absence. It is a particular kind of presence, the presence of space that has been organized by the same forces that organized everything else, shaped by the same ancient fluctuations, part of the same vast and intricate structure. To look into a void is not to look at nothing. It is to look at the universe from its quietest angle, where the web falls away and the scale of everything becomes for a moment almost imaginable. Chapter 7. Laniakea, our address in the cosmic web. For most of human history, the question of where we are in the universe had no satisfying answer. We knew the Earth orbited the Sun. We knew the Sun was one star among hundreds of billions in the Milky Way. We knew the Milky Way was one galaxy among countless others spread across the observable universe. But the question of where the Milky Way itself sits within the larger architecture of the cosmos, what structure it belongs to, what its gravitational neighborhood looks like at the larger scales, remained genuinely unresolved until surprisingly recently. The answer arrived in 2014, when a team of astronomers led by Brent Tully of the University of Hawaii published a paper in the journal Nature that redrew the map of our cosmic neighborhood in a fundamental way, using a new technique for tracing the boundaries of gravitational basins, regions of space whose matter flows toward a common center rather than draining away toward some other attractor. Tully and his colleagues defined for the first time the full extent of the supercluster that contains our galaxy. They named it Laniakea, from the Hawaiian words for immeasurable heaven. Laniakea is vast. It spans approximately 520 million light-years across and contains the mass of roughly 100 million billion suns. Within its boundaries sit approximately 100,000 galaxies, including the Milky Way, the Andromeda Galaxy, and all the other members of our local group. The Virgo cluster, which we touched on in the chapter on galaxy clusters, sits near the center of Laniakea, not at its absolute heart, but close to the gravitational core around which the supercluster's matter is slowly flowing. The technique that Tully and his team used to define Laniakea was based on measuring the peculiar velocities of galaxies, the component of each galaxy's motion that cannot be explained by the overall expansion of the universe and must therefore reflect local gravitational influences. By mapping these peculiar velocities across a large volume of space, the team was able to identify the boundaries where the direction of gravitational flow changes. Inside Laniakea, matter flows inward, toward the gravitational center. Outside it, matter flows away, toward other attractors. The boundary between these two flow regimes, called a basin of attraction divide, defines the edge of the supercluster. This was a genuinely new way of thinking about superclusters. Previously, superclusters had been defined by the positions of galaxies and clusters. Regions where the density of galaxies was higher than average were called superclusters, but the boundaries were always somewhat arbitrary, drawn by eye or by statistical threshold. Tully's approach defined superclusters dynamically by the gravitational flows that connect their members. A supercluster, in this framework, is not just a dense region. It is a gravitational watershed, a volume of space whose matter shares a common gravitational destiny. Our place within Laniakea is not central. The Milky Way sits on the outskirts of the supercluster, in a relatively underdense region, far from the Virgo cluster at the gravitational heart. We are, in the context of our own supercluster, something like a small town on the rural edge of a vast metropolitan region, present within the larger structure, subject to its gravitational influence, but not close to its center of activity. The peculiar velocity of the Milky Way carries it slowly in the direction of the Virgo cluster and the broader Laniakea interior, drawn by the same gravitational flow that connects all of the supercluster's members. The name Laniakea was chosen deliberately and carefully. Brent Tully, who has Hawaiian roots, worked with a Hawaiian language expert to find a name that captured the sense of the structure's scale and the difficulty of comprehending it, immeasurable heaven. It is a name that does not try to reduce what it describes to something manageable. It acknowledges the scale honestly, with a kind of respectful openness rather than false familiarity. Learning that we live inside Laniakea changes something about the sense of cosmic address in a way that is difficult to fully articulate. We have always known, abstractly, that the Milky Way is part of larger structures. The concept of superclusters has existed in cosmology for decades, but Laniakea gave that membership a name, a defined boundary, and a dynamic identity. It transformed the supercluster from a vague statistical feature into something with the character of a place, a specific, mappable region of the universe with a history, a gravitational personality, and a future. That future is worth noting briefly here. Laniakea is not a gravitationally bound structure in the way that a galaxy cluster is bound. The expansion of the universe, driven by dark energy, will eventually overwhelm the gravitational attraction that holds Laniakea's outer regions within its basin of attraction. Over tens of billions of years, the supercluster will disperse. The galaxies on its outskirts will drift beyond the basin divide and fall into the gravitational basins of other attractors. What remains bound, what will persist as a gravitationally coherent structure into the far future, is likely to be only the inner core, centered on the Virgo cluster, while the broader expanse of Laniakea gradually loses its identity as a single structure. But that dissolution is far in the future. For now, Laniakea is our home at the larger scale to which the word home can reasonably be applied. 100,000 galaxies, 520 million light-years across, flowing slowly toward a common center, bearing our small galaxy on its outskirts like a passenger on a very slow and very ancient journey. There is something grounding about knowing this, not in the sense of being made to feel small, though the scale does that easily enough, but in the sense of being located, of having an address that extends beyond the solar system, beyond the Milky Way, beyond the local group, all the way out to the supercluster scale. We are here, in this galaxy, in this group, in this supercluster, in this web. The coordinates are vast, but they are real, and they are ours. Chapter 8. The Great Attractor. There is something pulling us, not metaphorically, not philosophically, but physically. A gravitational influence so large and so persistent that it has been shaping the motion of the Milky Way and of every other galaxy in our region of the universe for billions of years. It sits in a direction of the sky, marked by the constellation Centaurus, partially hidden behind the dense star fields and dust clouds of the Milky Way's own disk, and for decades after its influence was first detected, astronomers could not see it directly. They could only measure its effects, the way galaxies across an enormous volume of space were moving toward a common point, pulled by something whose nature and extent remained frustratingly obscured. This gravitational anomaly is called the Great Attractor. The first serious evidence for the Great Attractor came in the 1980s, when a group of astronomers known informally as the Seven Samurai, Alan Dressler, David Burstein, Roger Davies, Sandra Faber, Donald Lynden Bell, Roberto Terlevich, and Gary Wegner, conducted a systematic study of the peculiar velocities of elliptical galaxies across a large region of the sky. What they found was unexpected. Hundreds of galaxies, spread across a volume hundreds of millions of light-years in extent, were not moving purely with the expansion of the universe. They had an additional component of motion, a bulk flow, directed toward a specific region of space in the direction of Centaurus. Something in that direction was exerting a gravitational pull strong enough to deflect the motion of galaxies across an enormous cosmic volume. The term Great Attractor was coined by Alan Dressler to describe whatever was causing this flow. At the time, its nature was entirely unknown. The region it occupied was behind the zone of avoidance, the band of sky obscured by the Milky Way's disk, where dust and stars make it extremely difficult to observe extragalactic objects at optical wavelengths. The Great Attractor was, in the most literal sense, hidden. Its presence was written in the motions of galaxies across hundreds of millions of light-years, but the thing itself could not be directly seen. Over the following decades, observations at wavelengths less affected by the zone of avoidance, particularly radio and X-ray wavelengths, began to reveal what lay behind the obscuring disk. What emerged was a picture somewhat more complex than a single massive object pulling everything toward it. The gravitational focus of the Great Attractor region turned out to coincide roughly with a large galaxy cluster called the Norma cluster, also designated Arbel 3627, sitting approximately 220 million light-years away. The Norma cluster is a rich, massive cluster with a bright X-ray emission characteristic of a deep gravitational well, and it sits at the heart of a broader concentration of galaxies and clusters that together constitute what is now called the Great Attractor region. But even the Norma cluster and its surrounding concentration of matter are not the complete story. As surveys pushed further through and beyond the zone of avoidance, a still larger structure began to come into view. Behind the Great Attractor region, at a distance of roughly 600 to 700 million light-years, lies the Shapley supercluster, the most massive concentration of galaxies in the nearby universe. The Shapley supercluster contains dozens of galaxy clusters and a total mass that dwarfs anything else in our cosmic neighborhood. Its gravitational influence extends across hundreds of millions of light-years, and it contributes significantly to the bulk flow that was originally attributed entirely to the Great Attractor. The current understanding is that the motion of the Milky Way and its neighbors reflects not a single attractor, but a combination of gravitational influences operating at different scales and distances. The Virgo cluster pulls us at relatively close range. The Great Attractor region, centered on the Norma cluster, exerts a stronger pull from further away. The Shapley supercluster contributes from even greater distances. And beyond Shapley, there are hints in the peculiar velocity data of still more distant mass concentrations whose full extent has not yet been mapped. This layered picture of gravitational influence is itself a reflection of the hierarchical structure of the cosmic web. Just as galaxies are embedded in clusters and clusters in superclusters, the gravitational influences acting on any given galaxy are also hierarchical. Local, regional, and large-scale forces all superimposed on one another, each operating at its own characteristic scale and contributing its own component to the total motion. What makes the Great Attractor story particularly compelling is what it reveals about the difficulty of measuring the universe from inside it. We cannot step outside our cosmic neighborhood and look at it from a neutral vantage point. We are embedded within the very structures we are trying to map, moving with them, carried by the same gravitational flows we are attempting to measure. Every observation we make is made from a platform that is itself in motion, influenced by forces that we are only gradually learning to disentangle. The Great Attractor was hidden, not just by the dust of the Milky Way, but by the fundamental challenge of doing cosmology from inside the cosmos. That challenge has not fully gone away. The zone of avoidance still obscures a significant fraction of the sky, and the structures behind it remain less well mapped than those in more accessible regions. New surveys using radio telescopes and infrared detectors are gradually filling in the picture, identifying galaxy clusters and filaments in regions that were previously blank on the map. Each new survey adds detail to a picture that is still, in important ways, incomplete. The Great Attractor is no longer the mystery it once was, but it retains a quality that resists easy summary. It is a reminder that the universe does not organize itself around our convenience as observers. It hides its most significant features behind the structures closest to us, requires patience and ingenuity to reveal, and rewards that patience not with simple answers, but with deeper questions about what else might be out there, pulling quietly from distances we have not yet learned to see clearly. Chapter 9. Beyond Laniakea. The larger structures. Laniakea is our home supercluster. It is the largest structure to which the Milky Way belongs in any gravitationally meaningful sense. But it is not the largest structure in the universe, or even in our immediate cosmic neighborhood. When you zoom out beyond Laniakea's 520 million light-year span, the view does not simplify. It becomes more complex, more populated, and in some ways more difficult to interpret. The universe beyond Laniakea is not a featureless expanse. It is a continuation of the same web, with superclusters and filaments and voids operating at scales that make Laniakea itself look like a regional feature on a much larger map. The first thing to appreciate when looking beyond Laniakea is that superclusters are not rare. They are not exceptional concentrations of matter separated by vast emptiness. They are the standard unit of large-scale structure, at the scale of hundreds of millions of light-years. The nodes and segments of the cosmic web at its intermediate scales, sitting above the level of individual clusters and below the level of the truly enormous structures we will explore in later chapters. The observable universe contains thousands of superclusters, each one a gravitational basin of the kind that Tully's team used to define Laniakea, each one containing hundreds or thousands of galaxies bound together by their shared gravitational history. Several superclusters in our extended cosmic neighborhood are well studied and deserve individual attention, both for what they tell us about large-scale structure in general and for the ways they relate to Laniakea specifically. The Shapley supercluster, which we encountered briefly in the previous chapter as a contributor to the Great Attractor flow, is the most massive supercluster in the nearby universe. It sits approximately 650 million light-years from the Milky Way, in the direction of the constellation Centaurus, and contains a concentration of galaxy clusters so dense that it has no close rival within the volume we can survey in detail. At its core are several rich clusters packed into a relatively small region, surrounded by an extended envelope of galaxies and groups that stretches across hundreds of millions of light-years. The total mass of the Shapley supercluster is estimated at more than 10 million billion times the mass of the Sun, a figure that makes even Laniakea seem modest by comparison. Its gravitational influence, as we noted, extends all the way to our own supercluster, contributing to the bulk flow that carries Laniakea and its contents in a slow drift across the cosmos. In the opposite direction from Shapley, roughly 300 million light-years from the Milky Way, lies the Perseus-Pisces supercluster. This is one of the most prominent large-scale structures in the nearby universe, a long chain of galaxy clusters and groups stretching across approximately 300 million light-years in a roughly linear arrangement that is one of the clearest examples of filamentary structure visible in galaxy surveys of our cosmic neighborhood. The Perseus cluster itself, sitting near one end of this chain, is one of the brightest X-ray sources in the sky and one of the most extensively studied galaxy clusters known. It is embedded in a rich intracluster medium whose X-ray emission has been mapped in fine detail by space-based observatories, revealing complex structures including ripples and cavities created by jets from the supermassive black hole at the center of the cluster's brightest galaxy. The Perseus-Pisces supercluster and Laniakea are separated by a void, a region of below-average density that sits between them and helps define their boundaries as distinct structures. This arrangement of superclusters separated by voids and connected by filaments is the basic pattern of the cosmic web repeated at the supercluster scale. Each supercluster is itself a node in a web of larger filaments, connected to its neighbors by bridges of matter that are thinner and less dense than the filaments within a supercluster, but nonetheless real and measurable. Further afield, at distances of around 1 billion light-years, the Hercules supercluster stretches across the sky as a loose, irregular concentration of clusters and groups less centrally concentrated than Shapley, but extended across a large volume. Beyond Hercules, the Corona Borealis supercluster presents another rich concentration of clusters at roughly 1 billion light-years distance, notable for the density of its core region and for the dynamical complexity of the cluster interactions within it. What begins to emerge when you catalogue these structures is a sense of the cosmic web as a genuinely three-dimensional architecture extending in every direction across the observable universe. Our supercluster is one node among many. The filaments that connect these superclusters are part of a network that has no center and no preferred direction. It looks, statistically, the same in every direction and at every location, at least on average. This statistical uniformity is itself an important cosmological statement, and we will examine it more carefully in a later chapter when we consider the cosmological principle and the structures that challenge it. For now, it is worth pausing on what it means to live in a universe so thoroughly structured at these scales. Every direction you look from the Milky Way, there are superclusters within 1 billion light-years, each containing hundreds of thousands of galaxies, each embedded in the same web that contains us. The universe is not a sparse scattering of matter in a mostly empty space. At the supercluster scale, it is a richly connected network, whose nodes are among the most massive objects in nature, and whose threads carry the gravitational memory of nearly 14 billion years of cosmic history. Laniakea is our home, but it is a home within a neighborhood, and the neighborhood extends further than we can currently map in full detail. The surveys that have revealed the structures described in this chapter represent decades of patient observational work, and they cover only a fraction of the observable universe. Beyond the well-mapped nearby volume, the web continues, same structures, same patterns, same physics, out to distances where our current instruments begin to lose the resolution needed to map individual superclusters and filaments. The universe does not end where our maps do. It continues, structured and vast, in every direction, for as far as light has had time to travel since the beginning. Chapter 10. The Sloan Great Wall and the Hercules-Corona Borealis. There is a category of structure in the cosmic web that sits above the supercluster scale. Features so large that they span not hundreds of millions but billions of light-years. Structures whose existence pushes against the boundaries of what current cosmological models predict should be possible. These are the Great Walls, and they represent the largest individual features that have been identified in the observable universe. To understand what they are and why they matter, it helps to approach them in sequence, beginning with the structures that were found first and working outward toward the ones whose scale remains, even now, difficult to fully reconcile with the standard picture of how the universe is put together. The first of the modern Great Walls to be identified was the CFA2 Great Wall, discovered in 1989 by Margaret Geller and John Huchra during the continuation of the redshift survey that had already revealed the broad filamentary structure of the nearby universe. The CFA2 Great Wall was a sheet of galaxies stretching across the survey volume at a distance of roughly 200 to 300 million light-years, spanning approximately 500 million light-years in its longest dimension. At the time of its discovery, it was the largest known structure in the universe, and its existence helped establish the reality of wall-like features as a distinct component of the cosmic web. Not just filaments and clusters, but extended planar concentrations of matter that form where multiple filaments converge along a common surface. The CFA2 Great Wall held its record for more than a decade. Then, in 2003, the Sloan Digital Sky Survey produced a map of sufficient size and resolution to reveal a still larger feature. The Sloan Great Wall, as it came to be called, stretches approximately 1.4 billion light-years in its longest dimension, making it nearly 3 times the size of the CFA2 Great Wall. It sits at a distance of roughly 1 billion light-years from the Milky Way and contains a chain of superclusters, clusters, and connecting filaments arranged in a roughly planar structure that spans an enormous arc across the survey volume. The Sloan Great Wall was immediately recognized as significant, and not only for its size. Its discovery raised questions about whether structures of this scale were consistent with the standard cosmological model, the lambda CDM model, which describes a universe dominated by cold dark matter and dark energy, and makes specific predictions about the statistical distribution of matter at large scales. The lambda CDM model predicts that the universe should become statistically uniform, homogeneous and isotropic, above scales of roughly 300 million light-years. Structures larger than that scale should not exist as coherent features, or at least should be so rare as to be effectively absent from the observable universe. The Sloan Great Wall, at 1.4 billion light-years, is considerably larger than that predicted homogeneity scale. Its existence does not necessarily invalidate the lambda CDM model. A single large structure, however impressive, can in principle arise as a statistical fluctuation, even within a model that predicts general homogeneity at large scales. But it prompted careful analysis of whether the standard model could comfortably accommodate such a feature, and those analyses produced somewhat mixed results. Some studies concluded that the Sloan Great Wall was within the range of structures that lambda CDM would occasionally produce. Others found it to be in mild tension with the model's predictions. The debate was inconclusive, partly because the statistical tools for evaluating the significance of a single large structure are themselves subject to methodological uncertainties. Then, in 2013, a structure was identified that made the Sloan Great Wall look modest. The Hercules-Corona Borealis Great Wall was discovered by Istvan Horvath, John Hakila, and Zsolt Bagoli, using the distribution of gamma-ray bursts, the extremely energetic explosions that occur when massive stars collapse or when neutron stars merge, visible across cosmological distances because of their extraordinary luminosity. By mapping the positions of gamma-ray bursts across the sky, the team identified a statistically significant excess of bursts in a region of sky spanning the constellations Hercules and Corona Borealis, at distances corresponding to a redshift of around 2, meaning light from this region has been traveling for roughly 10 billion years before reaching us. The estimated size of the Hercules-Corona Borealis Great Wall is staggering. Depending on the methodology used to define its boundaries, estimates have ranged from roughly 7 billion to 10 billion light-years in its longest dimension. To put that in context, the observable universe itself is approximately 93 billion light-years across. A structure spanning 7 to 10 billion light-years would occupy a significant fraction of the observable universe's total extent. It would be, by a very large margin, the largest structure ever identified. The Hercules-Corona Borealis Great Wall is also the most contested of the structures discussed in this chapter. Its identification rests on the distribution of gamma-ray bursts rather than on a direct galaxy survey, and gamma-ray bursts are relatively rare events whose positions carry significant statistical uncertainty. Critics of the discovery have argued that the apparent excess of bursts in the Hercules-Corona Borealis region could be a statistical artifact, a chance clustering that looks significant but does not reflect an underlying physical structure. Supporters have responded with refined analyses that they argue demonstrate the excess is real and robust. The scientific community has not reached a clear consensus, and the Hercules-Corona Borealis Great Wall remains, as of the time this video was made, a candidate structure rather than a fully confirmed one. What is not in doubt is that if the Hercules-Corona Borealis Great Wall is real, if the clustering of gamma-ray bursts in that region truly reflects an underlying concentration of matter, then it poses a serious challenge to the cosmological principle. A structure of 7 to 10 billion light-years cannot easily be accommodated within a universe that is supposed to become statistically uniform above 300 million light-years. It would require either a significant revision of the standard cosmological model or a deeper understanding of how such extreme structures can form within the framework that model provides. This is not a crisis for cosmology. The history of science is full of apparent anomalies that were eventually explained within existing frameworks, and it is also full of anomalies that eventually required those frameworks to be revised. The Hercules-Corona Borealis Great Wall may turn out to be one or the other. What it represents right now is an open question, one of several places where the map of large-scale structure pushes against the edges of current understanding in ways that are genuinely unresolved. The Great Walls, taken together, reveal something important about the cosmic web that is easy to miss when focusing on the more familiar scales of clusters and superclusters. The web does not simply repeat the same pattern at every scale. It has a hierarchy, and at the top of that hierarchy are features whose existence we are still learning to measure, whose physical status we are still debating, and whose implications for the standard model of cosmology we are still working out. The universe, even after decades of systematic survey, still holds structural surprises at its largest scales. Chapter 11: The Giant Arc and the Cosmological Principle. In 2021, an astronomer named Alexia Lopez, working toward her doctoral degree at the University of Central Lancashire, announced the discovery of a structure so large that it immediately attracted attention from cosmologists around the world. She called it the Giant Arc. It is a curved concentration of galaxies, galaxy clusters, and quasars spanning approximately 3.3 billion light-years, sitting at a distance of roughly 9.2 billion light-years from Earth. It stretches across more than 15% of the observable universe's diameter in its longest dimension, arranged in a shape that resembles, from our vantage point, a gentle curve or arc across the sky. The Giant Arc was found not through a dedicated search for large structures, but through a systematic analysis of the distribution of magnesium absorption systems, clouds of magnesium-rich gas associated with galaxies and their surrounding halos, detectable in the spectra of background quasars whose light passes through them on its way to our telescopes. By mapping the positions of these absorption systems across a large region of sky, Lopez identified a statistically significant concentration arranged in the curved pattern that gives the structure its name. The statistical significance of the detection, as reported in the discovery paper, was high enough that a chance alignment seemed unlikely. The probability of the arc appearing by random chance was estimated at around 1 in 10,000. The reaction from the cosmological community was a mixture of genuine interest and careful skepticism, which is exactly the appropriate response to a claim of this magnitude. The Giant Arc, if confirmed as a real physical structure, would be among the largest features ever identified in the observable universe, comparable in scale to the Hercules-Corona Borealis Great Wall, and similarly challenging to reconcile with the standard cosmological model's predictions about large-scale homogeneity. To understand why the giant arc and structures like it are theoretically problematic, it is necessary to spend some time with the cosmological principle, one of the foundational assumptions of modern cosmology, and one that has proven remarkably durable even as the universe has continued to reveal unexpected complexity at every scale we have examined. The cosmological principle states that the universe is, on sufficiently large scales, homogeneous and isotropic. Homogeneous means that it looks the same from every location. There are no special places, no centers, no edges where the density or composition of matter is fundamentally different from everywhere else. Isotropic means that it looks the same in every direction. There are no preferred axes, no directions along which the universe is structured differently than others. Together, these two properties imply that the universe, viewed at the right scale, is essentially uniform, a smooth distribution of matter and energy without large-scale gradients or preferred structures. The cosmological principle is not an observational result. It is an assumption, motivated by philosophical considerations as much as empirical ones, that has been built into the standard cosmological model from its foundations. It simplifies the mathematics of cosmology enormously, allowing the universe to be described by equations that apply everywhere rather than requiring a different description for every location. And for most of the history of modern cosmology, observations seem to support it. As surveys grew larger, the distribution of matter appeared to smooth out on the larger scales, approaching the uniformity the principle predicts. The homogeneity scale, the scale above which the universe is expected to look statistically uniform, is generally placed at around 300 million light-years in the standard lambda CDM model. Below that scale, structures of all kinds exist. Galaxies, clusters, superclusters, filaments, voids. Above it, the universe should look, on average, the same everywhere. The density of matter should not vary significantly from one large region to another. There should be no coherent structures, no walls, no filaments, no concentrations of any kind that extend across scales of billions of light-years. The giant arc, at 3.3 billion light-years, is more than 10 times the homogeneity scale. The Hercules-Corona Borealis Great Wall, at its estimated 7 to 10 billion light-years, is more than 20 times larger. If these structures are real, if they represent genuine physical concentrations of matter rather than statistical artifacts or projection effects, then they exist in a regime where the cosmological principle predicts they should not be found. This is the tension at the heart of the current debate about large-scale structure. It is not a simple tension with a simple resolution. The cosmological principle could be correct, and these apparent structures could be artifacts of the methods used to detect them. Statistical fluctuations that look significant but are not, or projection effects where matter at different distances along a line of sight creates the appearance of a coherent structure when none actually exists. Or the cosmological principle could be approximately correct, but with a homogeneity scale larger than current models predict, requiring adjustments to the standard model, but not its abandonment. Or, at the most radical extreme, the cosmological principle could be wrong in ways that require a fundamental rethinking of how we model the universe on the largest scales. Most cosmologists currently favor something in the middle of this range. The standard model has accumulated an enormous amount of supporting evidence from independent observations, the cosmic microwave background, the abundance of light, elements, the expansion history of the universe, the growth of structure at smaller scales. It would take more than a few anomalous large-scale structures to overturn it. But the anomalies are real enough to warrant serious investigation, and the field has been actively developing better statistical tools and larger surveys to address them. The giant arc is currently the subject of ongoing analysis. Follow-up studies have examined whether the structure can be explained by known systematic effects in the data, such as the non-uniform distribution of background quasars used to detect the magnesium absorption systems, or the possibility that the arc reflects a known large-scale structure seen in projection. Some analyses have found the giant arc to be robust against these concerns. Others have suggested that at least part of its apparent coherence may be attributable to observational biases. The question remains open. What the giant arc represents, regardless of how the debate about its physical reality is eventually resolved, is a genuine frontier in cosmology. It sits at the boundary between what we know and what we do not, between the well-mapped territory of clusters and superclusters, and the less certain terrain of structures so large that our current tools struggle to characterize them definitively. It is a place on the map where the label still reads, in effect, "Here be dragons." Not because the universe is hiding something deliberately, but because the instruments and methods needed to see clearly at these scales are still being developed and refined. There is something fitting about the fact that the universe continues to surprise us at its larger scales. It would be a lesser universe if it had given up all its structural secrets easily. The tension between the cosmological principle and the largest observed structures is not a failure of cosmology. It is cosmology working as it should, accumulating evidence, identifying anomalies, refining models, and moving slowly toward a clearer picture of a universe that is under no obligation to be simple. Chapter 12. How we map the invisible. Everything described in this video so far, the filaments, the voids, the superclusters, Laniakea, the great walls, is known to us through observation, not through theory alone, not through inference from first principles, but through the patient, cumulative work of measuring the positions and motions of galaxies across enormous volumes of space and assembling those measurements into maps. The cosmic web is not a theoretical construct that happens to match the data. It is something that was found in the data, something that emerged from the numbers before the theory was fully in place to explain it. Understanding how those maps are made, what techniques astronomers use, what instruments they rely on, what the maps can and cannot show, is essential to understanding what we actually know about large-scale structure and how confidently we know it. The most fundamental tool for mapping the cosmic web is the redshift survey. When light from a distant galaxy reaches our telescopes, it carries within it a record of how fast that galaxy is moving away from us. Because the universe is expanding, virtually all galaxies beyond our immediate neighborhood are receding, and the light they emit is stretched by that recession, shifted toward longer, redder wavelengths in a phenomenon called redshift. The amount of redshift in a galaxy's light tells us, with some important caveats, how far away the galaxy is. By measuring the redshifts of large numbers of galaxies across a region of sky, astronomers can construct a three-dimensional map of the galaxy distribution, not just where galaxies appear on the sky, but how they are arranged in depth, along the line of sight. The first systematic redshift surveys were conducted in the 1970s and 1980s, when the technology for measuring galaxy spectra had advanced to the point where redshifts could be obtained efficiently for large samples. These early surveys were limited in size, hundreds or a few thousand galaxies, but they were sufficient to reveal the first clear evidence of large-scale structure. The CFA Redshift Survey, conducted by astronomers at the Harvard-Smithsonian Center for Astrophysics, produced the famous slice of the universe maps that revealed the filamentary and wall-like distribution of galaxies in the nearby universe. Those maps, first published in the 1980s, were among the most visually striking results in the history of observational cosmology, and did much to establish the reality of the cosmic web in the minds of the astronomical community. The surveys that followed grew progressively larger and more systematic. The Las Campanas Redshift Survey in the 1990s extended the mapped volume significantly and confirmed the patterns seen in the CFA survey across a larger portion of the sky. Then, beginning in 2000, the Sloan Digital Sky Survey transformed the field entirely. The Sloan survey used a dedicated telescope at Apache Point Observatory in New Mexico, equipped with a special camera capable of imaging large areas of sky simultaneously, and a spectrograph that could measure the redshifts of hundreds of galaxies in a single observation. Over more than a decade of operation, the Sloan survey measured the positions and redshifts of hundreds of millions of galaxies, producing a map of the universe that covered roughly 1/3 of the entire sky and extended to distances of several billion light-years. The maps produced by the Sloan survey are among the most important scientific datasets ever assembled. They have been used to study virtually every aspect of large-scale structure: the clustering of galaxies on different scales, the properties of voids, the distribution of dark matter inferred from gravitational lensing, the large-scale velocity flows that reveal the gravitational influence of superclusters and great walls. They are publicly available and have been analyzed by hundreds of research groups around the world, producing thousands of scientific papers across a wide range of topics in cosmology and galaxy formation. But redshift surveys have limitations that are important to understand. The redshift of a galaxy is not a pure measure of its distance. It contains two components: the cosmological redshift due to the expansion of the universe, which does reflect distance, and the Doppler redshift due to the galaxy's peculiar velocity, its motion relative to the overall expansion flow caused by local gravitational influences. These two components cannot be separated directly from a single redshift measurement. In regions where peculiar velocities are large, inside galaxy clusters, for example, where galaxies are moving rapidly through a deep gravitational well, the apparent positions of galaxies in redshift space are distorted relative to their true positions in real space. Clusters of galaxies appear elongated along the line of sight in redshift maps, a visual artifact called the finger of God effect, because the range of peculiar velocities within the cluster spreads the galaxies out in the redshift dimension, even though they are physically compact in three-dimensional space. On larger scales, the coherent infall of matter toward overdense regions produces a different kind of distortion, a compression of structures along the line of sight that slightly alters their apparent shapes in redshift maps. These redshift space distortions are not simply a nuisance to be corrected for. They contain valuable information about the rate at which structure is growing, which in turn constrains the properties of dark matter and dark energy. Extracting that information requires careful statistical modeling of how peculiar velocities relate to the underlying density field, and it has become one of the most productive areas of large-scale structure research. The peculiar velocity surveys used to define structures like Laniakea represent a complementary approach to redshift surveys. Rather than simply mapping where galaxies are, peculiar velocity surveys measure how galaxies are moving. the component of their motion that deviates from pure Hubble expansion. These measurements are more difficult to make than redshift measurements because they require independent distance estimates for each galaxy that do not rely on redshift. Several methods exist for making such estimates. The Tully-Fisher relation, which connects the rotation speed of a spiral galaxy to its luminosity, and the fundamental plane relation for elliptical galaxies are among the most widely used. But all of them carry significant uncertainties that limit the precision of the resulting velocity maps. The Cosmic Flows project, led by Brent Tully and his collaborators, has been the most systematic effort to compile peculiar velocity data across the nearby universe. The project has assembled catalogues of galaxy distances and peculiar velocities that have grown through successive data releases. Cosmic Flows 1, Cosmic Flows 2, Cosmic Flows 3, and Cosmic Flows 4, each larger and more precise than the last. It was the Cosmic Flows data that provided the velocity field used to define Laniakea in 2014, and subsequent releases have refined and extended the picture of the local velocity field in ways that continue to reveal new details about the gravitational structure of our cosmic neighborhood. Beyond observational surveys, computer simulations have played an increasingly central role in our understanding of the cosmic web. Simulations like the Millennium Simulation, run in 2005 by Volker Springel and collaborators at the Max Planck Institute for Astrophysics, model the gravitational evolution of hundreds of millions of dark matter particles from the early universe to the present day, producing virtual universes whose large-scale structure closely resembles what is observed in real galaxy surveys. More recent simulations, including the Illustris project, the Eagle simulation, and the TNG series, have added the physics of ordinary matter, modeling the formation of galaxies, the heating and cooling of gas, the feedback from supernovae and active galactic nuclei, all within the context of a cosmologically realistic large-scale structure. These simulations serve multiple purposes. They allow cosmologists to test whether the standard model of cosmology produces the observed large-scale structure when run forward from initial conditions constrained by the cosmic microwave background. They provide a framework for interpreting observations, helping to distinguish between genuine physical structures and artifacts of the observational process. And they make predictions about aspects of the cosmic web that have not yet been observed. The properties of filaments at high redshift, the internal structure of voids, the nature of the dark matter halos that host galaxies in different environments, that can guide the design of future surveys. The maps we have of the cosmic web today are the product of this combination of observation and simulation, each informing and refining the other over decades of work. They are incomplete. Large portions of the sky remain poorly surveyed, and the surveys that exist lose resolution at high redshifts, where individual galaxies become difficult to detect and characterize. But within their limits, they reveal a universe whose large-scale architecture is more intricate, more hierarchical, and more surprising than anyone anticipated when the first redshift surveys were conducted half a century ago. Mapping the invisible is slow work. It requires patience, precision, and the willingness to spend years accumulating data that will only reveal its full meaning when assembled into a picture large enough to show the structure hidden within it. The astronomers who built the surveys described in this chapter did not know, when they began, exactly what they would find. They found the cosmic web, not because they were looking for it specifically, but because they were looking carefully, and carefully enough, and long enough, that the universe eventually showed them what was there. Chapter 13. simulating the web. There is a particular kind of knowledge that comes not from observing the universe directly, but from building a version of it inside a computer and watching what happens. It is not the same as observational knowledge. It depends on assumptions, on the physical models written into the simulation's code, on the accuracy of the initial conditions fed into it at the start. But it is not merely theoretical either. A good simulation makes predictions that can be tested against observations, reveals structures and processes that observation alone could not have anticipated, and provides a way of understanding not just what the universe looks like, but why it looks that way. What physical processes, operating over what timescales, produce the structures we see when we look outward from our small corner of the cosmic web. The history of cosmological simulation is a history of growing ambition, meeting growing computational power. The earliest simulations, run in the 1970s and 1980s, could follow the gravitational evolution of only a few hundred or a few thousand particles, each particle representing an enormous mass of dark matter, the small-scale details of galaxy formation far beyond the reach of the available computing resources. These simulations were nonetheless valuable. They demonstrated that a universe beginning with small density fluctuations and dominated by cold dark matter would naturally develop the filamentary structure observed in galaxy surveys. The cosmic web, in other words, was not just found in the data. It was predicted by the simulations before it was fully mapped by observation. As computing power increased through the 1990s and into the 2000s, simulations grew in both size and resolution. The number of particles that could be followed increased from thousands to millions to billions. The volume of simulated universe grew from boxes a few 100 million light-years across to boxes spanning several billion light-years. The physical processes included in the simulations expanded beyond pure gravity to encompass the hydrodynamics of gas, the formation and evolution of stars, the feedback of energy from supernovae and active galactic nuclei into the surrounding gas. Each generation of simulation revealed new aspects of large-scale structure that the previous generation had lacked the resolution or the physical complexity to capture. The Millennium Simulation, completed in 2005 by a team led by Volker Springel at the Max Planck Institute for Astrophysics in Garching, Germany, represented a turning point in the field. It followed the gravitational evolution of approximately 10 billion dark matter particles within a simulated cube roughly 2 billion light-years across, producing a virtual universe whose large-scale structure, its filaments, its clusters, its voids, closely resembled the structure revealed by the Sloan Digital Sky Survey. The Millennium Simulation was not the first cosmological simulation, nor was it the largest by later standards, but it was produced at a moment when observational data had become rich enough to compare against in detail, and the agreement between the simulation and the observations was striking enough to generate significant confidence in the overall framework of the lambda CDM model. What the Millennium Simulation showed, among many other things, was the hierarchical nature of structure formation in vivid detail. Small halos of dark matter formed first, in the densest regions of the early universe. These small halos merged to form larger ones. The larger halos merged to form still larger ones. Filaments assembled along the axis of density fluctuations inherited from the cosmic microwave background. Voids evacuated as matter drained toward the growing halos and filaments. The entire process unfolded in the simulation over simulated billions of years, driven entirely by gravity acting on the initial conditions, producing a universe that looked, at the end of the run, remarkably like the one we actually inhabit. One of the most visually striking outputs of large cosmological simulations is what has become known as the cosmic web visualization. Rendered images of the dark matter distribution that show, with extraordinary clarity, the filamentary network connecting bright halos against the dark background of the voids. These images have become among the most widely reproduced in all of science, appearing in textbooks, documentaries, and popular accounts of cosmology around the world. They have a quality that is immediately recognizable and deeply arresting. The web looks organic, almost biological, like something that grew rather than something that was calculated. The resemblance to neural networks, to fungal mycelium, to river deltas seen from the air, is not coincidental in any deep sense. It reflects the fact that branching, hierarchical networks are a common product of processes involving flow and accumulation, whether the substance flowing is dark matter under gravity or water under topography. The simulations that followed the millennium pushed further in every direction. The Illustrious simulation, completed in 2014, modeled a volume of space roughly 350 million light-years across, with sufficient resolution to follow the formation of individual galaxies, including the growth of their stellar populations, the evolution of their gas reservoirs, and the influence of feedback from central black holes. Its successor, the Illustrious TNG series, refined the physical models and extended the simulated volume, producing a suite of simulations at different scales and resolutions that have been used to address a wide range of questions about galaxy formation and large-scale structure simultaneously. The Eagle simulation, developed by a consortium of European institutions and first published in 2015, took a similar approach, modeling a cosmologically representative volume with sufficient resolution to study individual galaxies, but with somewhat different implementations of the physical processes involved in star formation and feedback. Comparing the results of Eagle and Illustrious TNG with each other, and with observations, has been informative about which aspects of galaxy formation are robust predictions of the overall framework and which depend sensitively on the details of the physical models used. One of the most important uses of these simulations has been to understand the relationship between the visible cosmic web, the distribution of galaxies revealed by redshift surveys, and the underlying dark matter web that the galaxies trace. Because dark matter cannot be observed directly, the only way to infer the full three-dimensional distribution of dark matter from galaxy surveys is to use simulations as a guide. Simulations tell us how galaxies are expected to populate dark matter, halos of different masses, in different environments, at different epochs. This knowledge allows astronomers to work backward from the observed galaxy distribution to the inferred dark matter distribution, a process called halo occupation modeling or abundance matching, depending on the specific technique used. Simulations have also been essential for understanding the warm-hot intergalactic medium, the diffuse gas in filaments that we discussed in the chapter on filamentary structure. Because this gas is so diffuse and so hot that it emits only weakly at most wavelengths, direct observational mapping of the filamentary gas is extremely challenging. Simulations predict its distribution, its temperature structure, and its density profile with considerable precision, and those predictions guide the design of observational programs aimed at detecting it. When observations do detect filamentary gas, the comparison with simulations provides a way of testing whether the overall picture of cosmic web formation is correct in its details as well as its broad strokes. Perhaps the most ambitious simulation project currently underway is the Euclid Mission's Associated Simulation Program, designed to support the interpretation of data from the Euclid Space Telescope, which was launched in 2023 and is conducting a survey of the large-scale structure of the universe across a volume far larger than any previous survey. The simulations associated with Euclid are among the largest ever attempted, designed to match the survey's enormous volume while maintaining sufficient resolution to model the galaxy populations that the telescope will observe. They represent the current frontier of cosmological simulation, a frontier that continues to advance as computing technology improves and as our understanding of the relevant physics deepens. There is something philosophically interesting about the role that simulation plays in modern cosmology. We cannot run the universe again from the beginning with different parameters to see what would happen. We cannot travel to a different part of the cosmos and observe large-scale structure from a different vantage point. We are stuck here, in this galaxy, on this planet, looking outward with the instruments we have managed to build. Simulation gives us a way of exploring counterfactuals, of asking what the universe would look like if the dark matter density were different, if the primordial fluctuations had a different amplitude, if dark energy had a different equation of state. It extends our reach beyond what observation alone can access, into the space of possibilities that lies around our actual universe. That extension comes with responsibilities. The results of a simulation are only as trustworthy as the physical models and initial conditions built into it. Every simulation makes choices about what physics to include, what to approximate, what to ignore. And those choices shape the results in ways that are not always easy to disentangle from the genuine physical predictions. Good simulation science is aware of these limitations, tests its results against observations wherever possible, and is honest about the boundaries between what is robustly predicted and what depends on modeling choices that could reasonably have been made differently. Within those boundaries, cosmological simulations have been among the most productive tools in the study of the cosmic web. They have confirmed the broad outlines of how the web formed, revealed the physical processes that shape it, and produced predictions that have guided and been tested by observations across multiple decades. The universe inside the computer is not the universe, but it is close enough, in the ways that matter most, to have taught us a great deal about the one we actually live in. Chapter 14. The Web at the End of Time. Nothing in the universe is permanent. The cosmic web, for all its scale and all its apparent solidity, is not a fixed structure. It is a moment in a process, a snapshot of matter arranged in a particular way at a particular point in cosmic history, subject to forces that will, over timescales almost beyond imagination, pull it apart and leave something entirely different in its place. To understand the future of the cosmic web, it helps to consider the force that will ultimately determine it. Not gravity, which built the web and continues to hold its densest regions together, but dark energy, the mysterious component of the universe that is causing space itself to expand at an accelerating rate. Dark energy was discovered in 1998, when two independent teams studying the brightness of distant supernovae found that the universe's expansion was not slowing down, as everyone had expected, but speeding up. Something was pushing space apart faster and faster, overcoming gravity on the larger scales and driving galaxies away from one another at ever-increasing velocities. The nature of dark energy remains one of the deepest unsolved problems in physics. It may be a property of space itself, a kind of energy inherent in the vacuum that does not dilute as the universe expands. It may be a dynamic field that changes slowly over time. It may reflect a modification of gravity at the larger scales. Whatever it is, its effect on the cosmic web's future is clear in broad outline, even if the details depend on its precise nature. In the relatively near term, over the next few billion years, the web will continue to evolve much as it has been evolving. Filaments will continue to drain matter toward clusters. Clusters will continue to grow more massive as they accrete material from their surroundings. Voids will continue to expand, pushing outward against the filaments that bound them. The broad architecture of the web will persist, recognizable in its outlines even as its details change. But on longer time scales, the accelerating expansion will begin to overcome the gravitational bonds that hold the larger structures of the web together. Superclusters, which are not gravitationally bound in the way that clusters are, will gradually dissolve. The galaxies on the outskirts of structures like Laniakea will drift beyond the basin of gravitational attraction that currently defines the supercluster, pulled away by the expansion faster than gravity can draw them back. What remains bound, the inner cores of superclusters, anchored by the deep gravitational wells of massive clusters, will persist, but the extended filamentary connections between them will thin and eventually fade as the galaxies strung along them disperse into the growing voids. Further into the future, the expansion will isolate gravitationally bound structures from one another entirely. There will come a time, tens of billions of years from now, when the galaxies beyond our own local group will have receded so far and so fast that their light will no longer be able to reach us. The observable universe, as seen from the Milky Way, will shrink, not because space is contracting, but because the expansion is carrying distant galaxies beyond the cosmological horizon faster than light can cross the growing distance between us. One by one, the galaxies we can currently see will fade from view, redshifted beyond detectability, lost behind a horizon that retreats faster than any signal can follow. In the very far future, the local group itself, the Milky Way, Andromeda, and their smaller companions, will merge into a single large elliptical galaxy, the product of the slow gravitational inspiral that has been underway for billions of years already. That merged galaxy, sometimes called Milkomeda in informal usage, will be gravitationally bound to the remnants of the Virgo cluster and the inner core of what was once Laniakea. Together, they will form an island, a gravitationally bound structure surrounded by an expanding void that grows larger with every passing billion years, containing nothing but the fading light of galaxies too distant to ever be reached again. The cosmic web, as a connected structure spanning hundreds of millions of light years, will not survive into the deep future. It is a feature of this particular era in cosmic history, an era when the universe is old enough that gravity has had time to assemble the web from the small fluctuations of the early universe, but young enough that the accelerating expansion has not yet had time to pull the web's larger structures apart. We exist at a fortunate moment, in this sense. We can see the web. We can map it, study it, trace its filaments and clusters and voids across a significant fraction of the observable universe. Civilizations arising in the very far future, if any do, will inherit a far lonelier cosmos, one in which the evidence for the web's existence will have largely dispersed, and the universe will appear to consist of nothing but a single bound island of stars surrounded by an empty and ever-expanding darkness. There is a particular kind of quiet that comes from sitting with this thought. Not sadness exactly, more like the feeling of appreciating something beautiful in the knowledge that it is temporary, which is, in the end, the condition of everything worth appreciating. The cosmic web exists now. It is real and vast and intricate and ancient, Its filaments carry matter across hundreds of millions of light years. Its voids hold the memory of the early universe in their expanding emptiness. Its clusters burn with the X-ray light of superheated gas and the slow orbital motion of thousands of galaxies. And somewhere within it, on the outskirts of a supercluster called Laniakea, in a small spiral galaxy on an unremarkable arm, something has arisen that is capable of looking outward, measuring the web, understanding how it formed, and recognizing, with a sense of wonder that seems entirely appropriate to the scale of what it has found, that it is part of it. The web is not out there, separate from us. We are woven into it. We have always been.